So I'm now going to start on confidence intervals for proportions. So we've now done a whole lot of stuff on standard errors for the median of various kinds of measurements. The next one I want to talk about is proportions. So once you know how to do it for medians and proportions, there's a lot of applications for these. So the story with proportions is, it's just like what we've done with medians. We have a way of calculating a standard error for a proportion, and then once we've got a standard error, we can calculate a 95% confidence interval. Okay, it's just the proportion plus or minus 1.96 times the standard error. Okay, so that part of it's exactly the same. The thing that's different is the formula for doing the calculation for the standard error, which is a little bit more complicated. So I'll start. I think we've got time today to cover it, so let's see how we go. All right, so let's look at an example. This is about cats that are mostly black. Okay, so there's an example there. That's my cat, and he is mostly black. He has one little white spot. Now, I got the idea from this example when I learned that in the United States, the business of rescuing cats and finding new homes for them is actually, the biggest player in that is not a charity or an NGO, it's a private company. I've forgotten the name of it, but it's owned by Nestle. It's a big business. And it is no doubt motivated by profit, and people in that business would be paying quite a lot of attention, I think, to the sort of pets that can be easily rehomed, is the term they use, given a new home. So let's say you're developing a business case for a new venture in Australia that will do this, and you talk to, we have this organisation in Australia called the RSPCA, which is an animal welfare NGO, and one of the things it does is, it's a charity, one of the things it does is it rehomes animals, including cats. So they tell you that about 70% of the cats they get, they're able to find new homes for, and the other 23% they can't, and they are euthanized. Now, you've been doing research on this, and you've talked to people and who work in this area, and they'll tell you, look, the easiest ones to rehome are kittens. Everyone wants a cute kitten, and the hardest are these adult, mostly black cats with a bit of white on them. Okay, they say they're hard to rehome, and we think the reason they're hard to rehome is mainly because of social media these days. Everyone wants to get a cat and take selfies with it, and take pictures of it and put them on Instagram and TikTok and whatever. And the problem with black cats is they're very hard to photograph well. Black fur doesn't photograph well with phones, and in some countries black cats are associated with witchcraft and bad luck and so on. So that's just anecdotal stuff. So you want to get a better idea of what proportion of these predominantly black cats, we sometimes call them tuxedo cats, the ones with a bit of white on the front of them, what proportion are rehomed. So you're able to get hold of a sample for 120 cats, a random sample from the previous calendar year, and you learn that only 72 of those 120 were rehomed. So what you want to do, you've got a sample, you want to estimate the proportion of these type of cats among the whole population from which the sample was drawn, of rescue cats that are rehomed. And so your first thing you've got to do is, well, you've got to calculate the proportion of the sample, and you need to calculate a standard error. So let's go through some of the issues here. There's a bit of terminology we need to get across. So the proportion here, the raw or the initial proportion, we'll use lowercase p, that's typically used, is 72 over 120, so that's 0.6, and the sample size n is 120. You'll see I'm using lowercase n here, and sometimes I use uppercase. There's no particular significance to that. some people use one, some use the other. Now, let's get a few facts and bits of terminology. So proportions can be expressed as percentages. So in this case, the proportion that is rehomed is 60%, 0.6. Proportions can only have values between 0 or 1, or between 0% and 100%. Sometimes when you calculate confidence intervals, you'll get a lower bound on the confidence interval, or sometimes an upper bound, that are outside that range of 0 to 1. So if, for example, we calculated a confidence interval for a proportion and the lower bound was minus 0.2, that makes no sense, so we would just make it 0. And similarly, if we got an upper bound for a confidence interval that was 1.1, we would truncate that back to being 1. So I'm just warning you that sometimes can happen, and that's how you respond to it. The second thing is a terminological thing. So in statistics, when people are talking about proportions, they use the term success and failure, and they're using that in a technical way. So in our case, we're interested in the proportion of cats who are rehomed, and so we would say there are 72 successes and 48 failures. 72 plus 48 makes up our sample of 120. But the term success actually has nothing really to do with the outcome that we're interested in the kind of real world would be regarded as a success. So the example I give here is if we were interested in mortgage defaults and we had a sample of 100 mortgages and 30 of them were in default, we would say there were 30 successes and 70 failures. So the thing we're focused on is the defaults. So that's what we think of as the successes in a technical statistical sense. So that's just a matter of terminology. You probably don't need to worry about it too much in your normal usage, but if you, for example, were using statistical software to do some kind of analysis of proportions, it's very likely the software would ask you to tell it how many successes were there and how many failures. And then you need to know what the technical meaning of success and failure is. So I'm just mentioning that, not something I'm going to test, but useful to know about. Now, in the formula that we're going to get to in a moment, the denominator, the bit on the bottom, is the square root of n, and that's the same. Our formula for the standard error of the median also has the square root of n on the bottom, and that's pretty typical of standard error formulas. So what that means is that the size of the standard error gets smaller in proportion to the square root of the sample size. And I've talked about this before. Basically, if you want to shrink the standard error by half, you've got to increase the sample size by 4 times. Now the numerator in the formula, so here's the first version of the formula, is the square root of the proportion of successes multiplied by the proportion of failures. Okay, so the first way I've written it, it looks like that. So you've got square root of n on the bottom, and you've got the proportion, that's 0.6, multiplied by the proportion of failures, that's cats that were not rehomed. So that's 1 minus 0.6, that's 0.4 or 40%. So you multiply those, find the square root of them, and then you divide that by the square root of n. So that's one way of writing the formula. It's not the most common way, but I've just done it that way to sort of emphasize the fact that square root of n is on the bottom. The way that it's normally written, which is mathematically equivalent, is this second version here. And this version of it, this is known as the Wald estimate, W-A-L-D. And this is what you'll see in all the textbooks. This is the most common way. I learnt this as an undergraduate. It's still in all the textbooks. If you've done an introductory statistics course, you've almost certainly learned this formula. The problem with this formula is that it can be unstable under certain circumstances, usually when the proportions are very small or very big. Okay, and this fact has been known for a while, but that kind of hasn't stopped people using it. So there is a better version, and that's the one that we're going to use. which has a little modification to it. So the version we're going to use is known as the Agresti-Cool estimate. It's named after the two statisticians who first published the idea. Agresti is a big name in statistics. He's you mention his name, anyone who's into statistics will recognize him. So the change is just you make an adjustment to the proportion and the sample size. And the adjustment's very simple. So you add 2 to the successes. The effect of it is you add 2 to the successes and you add 4 to the sample size. Okay, and so we represent these, the convention is you represent these adjusted versions by putting a little squiggle, a tilde it's called, on top of the sample size and the proportion symbol. So the adjusted sample size is n plus 4, so that's 120 plus 4, which is 124. And the adjusted proportion is 72 plus 2 over 124. Okay, 72 over 124, 0.597. So that's the adjustment. Once you've made that adjustment, you then just do the calculation. So let's do it. That's the calculation there. So we're going to multiply the adjusted proportion, which is 0.597 rather than 0.6, and we multiply that by 1 minus 0.597, and then we divide that by 124 and we get 0.044. So that's our standard error. And now that we've got the standard error, we proceed exactly as we did with the confidence interval for the median. I've written it here as the proportion, so the adjusted proportion plus or minus 1.96 times the standard error. And if you work that out, which I've done there, we can say that we are 95% confident that the proportion of predominantly black cats that are rehomed in Australia is between 51% and 68%. So remember, the original proportion was 0.6. The adjusted confidence interval is between 51%, 0.51, and 68%, 0.68. So that's all there is to it. There's basically 2 things to remember. So one is to do this little add 2 and add 4 adjustment, and then you just use the standard widely known formula for the standard error for proportions, and then you calculate the confidence interval in the usual way. Now, one thing I should say about that adjustment, that add 2 and add 4 adjustment, is that is designed to work with 95% confidence intervals. But I think you'll find in real life they're probably just about the only confidence intervals you ever work with, so that's not too much of a problem. If you want to do the adjustment for some different confidence interval, there's a little bit more work to do, but I don't think we need to worry about that. All right, let's now I want to well, how are we going? We don't have a lot of time left. We might try and do one example here. Maybe I should leave this till next week. I think what I might do is I've just put two examples there. I think I might go through those next week, but I'll just talk a little bit about what you do with them. The first one here, so this is a pretty common thing that happens in real life. Somebody comes to you and they've done some sort of survey. It's not a very big response rate, and they start quoting proportions. Now, a really important thing to know about proportions is when the confidence intervals for proportions tend to be quite a bit wider than you might expect, especially if you're just used to doing t-tests or our median test and getting confidence intervals for means or medians. Proportions tend to, particularly with small sample sizes, come up with very wide confidence intervals. And if you do the calculation, I would strongly recommend you do this calculation, try it out. And I'll go through the answer next week, but you will find that the confidence interval, the initial proportion is 75%, but the confidence interval is pretty wide. That's a thing that you ought to be very aware of when you're dealing with proportions. The second example I've given you here, so this is based on real data. The sample size is a bit bigger here. It's 187, so the proportion of interest here is 46%, 86 respondents out of 187. But again, if you do the calculation, you'll find that the confidence interval is still fairly wide. So that's a kind of important thing to learn from this, because you come across proportions all the time, and particularly whenever anyone does a survey. When people are writing up reports of surveys, they're always talking about the percentage of people who said this and the percentage of people who said that, and so on. And when we do surveys, we're nearly always actually surveying what is supposed to be a representative sample of somebody. And if you know how to do this, then you can do an estimate of the precision of those proportions. And let me tell you, it's often going to be disappointing. Okay, they're going to be pretty wide. I haven't done it, but I'm pretty confident if I did the confidence intervals for student evaluation scores, given that the samples are usually pretty small, they're usually about somewhere between 10 and 20% of a class, the confidence intervals would be really wide. So that's an important takeaway here. All right, so that was everything for today. Tomorrow's tutorial is going to be about searching on Web of Science as part of the critically appraised topic process. So if you can come along, that would be great. Otherwise, I'll be doing the recordings as usual. So I'll wrap up there. Happy to stay around for questions. Otherwise, we'll call it a day.